Hello and welcome to Advent of Code 2016. We're really in the final stretch now. Only 3 problems left. Excited to see what these problems are. About 8 seconds left to go before it becomes available. And here we go. Safe cracking. All right. Okay. Digital screen. Password hint is eggs. 7 eggs. When you go to type the code, key part smashed. It's a prototype computer. A SEM-bunny. All right. That the monorail. Okay. All right. So it looks like we wanna grab this stuff. All right. Let's take a look here. With one new instruction is a toggle. So it toggles the instruction XOA. Okay. Okay. So this is a self-modifying program. All right. Well, let's take a look at JNZ. All right. Okay, we got do instruction, halted, this thing called value, it's got a starting state, we got a parser. All right, so I think something like this here, and then do we need any more? Maybe not. All right, so let's paste this in down here. Toggle X. Okay, so we should be able to modify this code here. So yeah, let's see. So I think we basically want to say put in TGL state, and then basically we want to say, how do we want to do this? So I think we sort of want to represent our, change the way this is represented here. Say keys state code like this, and then because we have to treat code as state right now. And then we'll call this computer, something like that. And then basically increment, this needs to be update in state here. And then this also needs to be an update in state like that. Okay. Update in state there. Update in state here. Okay, our copy. So this needs to be assoc in like this. Update in that. Okay. Okay, and then this is the last one here. So update in computer state the instruction pointer. Update in computer state the instruction pointer. All right. Okay, so now we have to know how to do a toggle on a computer. So we go into computer, and then we say something like toggle the value in state of arg_a of the instruction. Yes. Okay. Right. So toggle takes this same thing here, and an additional argument, which is this is going to be some x. All right, so we need to add x to, how do we, so we can just get I out of state like this. Looks good. So add these together. And then, so we need to say update in, to take the computer, actually, yeah, okay, we'll just do it this way. Take the computer, update in, actually, what is the question here? What value should be sent into the safe? Okay, got it. So we do need to run this program. Okay, so update in, so the code, this instruction here, and now we need to write a function from, so this is going to be, keys are going to be operator, arg A, arg B. All right, so what does toggle actually do? For one argument instructions, inc becomes dec, and all other one argument instructions become inc. So let's see. I think we say, so let's put cond in here. So if arg B is nil, then we say if we're dealing with an inc, then we want to emit SOS. All right, so this, we're going to call this the instruction. SOS, the instruction, we're going to change the operator to dec. And otherwise, we're going to change the operator to an inc. All right. Good. Next case in the cond is going to be, if an attempt is made to toggle an instruction outside the program, nothing happens. So we would want to say, so actually what happens if we try to do update in this one constantly, something like this. Okay, so this is not a bounds exception, so we need bounds checking on here. So we need to say something like if get if this number is at least as great, or we'll say here this is less than the count of the code here, and we're going to do all this stuff. Otherwise, we're just going to return the computer. Nothing happens. All right. Okay. So if toggling produces an invalid instruction and an attempt is made later to execute that instruction, skip it instead. All right. So we're going to have to figure out which instruction, how an instruction would be invalid. And let's see. If toggle toggles itself, for example, if A is 0, the resulting instruction is not executed until the next time it's reached. Okay, so let's see. Toggle toggles the instruction that many way. Okay, our computer wouldn't do this anyway. Okay. All right, so then we just have to handle a 2 argument case. A and Z becomes copy, and all other instructions become, okay, so it's just this sort of thing. Same sort of here. Else, it's a J and Z, then this becomes CPY, and otherwise it becomes J and Z. All right, so I don't know if we actually need to, let's see, how can instructions be invalid? I guess incrementing or decrementing at something that isn't a register, but I don't think that we really care about that because It'll just be modifying things that that don't change. Oh, one thing that we have to do is bump our instruction counter for sure. All right. Okay, so let's try loading all this EOF while reading. Up here, let's see, so that, there. Okay, this looks good. All right, so let's see, do I have my old reduce here? Looks like I do have, I did define starting state. Do I have starting state up here? I do, good. Good, so reduce, let's grab this here. Don't need this. Oh yeah, let's take a look at, oh, so where's code supposed to come from? So actually we need a new starting state here. So the new starting state is going to be one where state is this and code is map the parse to, let's start with this, the board lines. Okay, so let's get the starting state here just to verify this looks good. Yeah, it looks pretty good. All right, and then I'm gonna, yeah, okay, this is fine. All right, so then iterate on do instruction, filter halted. Okay. Looks like we don't use that. Yeah, let's just try running it. Unable to resolve symbol. Oh, right. Yeah. Yeah. So let's see, filter. Oh yeah, so actually we do need halted. So we need to implement this. Basically, if the keys are state and code. Okay, recognize that situation. So now we can just say filter halted, iterate do instruction. Doesn't this look a lot better? All right, so let's try this. This gave us something out. Final value in register A is 3. Okay. A, run the code, send the value left in register A to the safe. Okay, get our puzzle input. Here we go, and run the whole thing. Okay. All right, not getting anything back yet. In the last problem, I know that there was a little optimization that was possible to be made. I'll let this run for a little while longer. Take a look at the examples here. Second toggle, the rest of the electronics seem to place the keypad entry in register. Oh, I see. Wait, hang on. The rest of the electronics seem to place the keypad entry. So 7. So A has got to start as 7. So let's do this. Let's go up to our starting state here, and then we have to associate A as 7, like this. And then does it specify the other starting states? I guess they're all just supposed to be 0 except for A. All right, so let's get puzzle input again. Oh, I see. All right, grab this. Okay, run this whole thing. Oh, interesting. Okay, so this looks like the value of A. The right answer, rank 19. Nice. All right. Safe doesn't open, but does make angry noises. Your logic is good. Colored eggs, okay, but it's actually 12. Begins to overheat. You wonder what's taking so long and whether the lack of don't bunnies usually multiply. Yeah, anyway, what value should actually be sent to the safe? Okay, I do remember this. It's basically using the JNZ and ink and deck in order to make a multiply. So we have to, what can we do? I think let's stare at this for just a little while. I think that this kind of construct here, if you have ink, deck, JNZ, neg2, then this construct right here is a multiply. This construct is, oh, is it a multiply? No, it's an add. So this construct is add the value in this to this. So I wonder if we could define like an optimizer. So, all right, I'm pretty sure that if I change this to 12 up here, then my result is just gonna, it's just gonna go for, F1 so that I don't overwrite it. But hope springs eternal. So let's pop this in here. Okay, so what are we gonna do? I think that we need that maybe what we can do is something like so like optimize, which takes code. And then we want to do something. So let's say we want to implement that. Then we want to do something like do a partition. Let's see. Be right back. I need to plug in. All right. So we want to do a partition and basically look for this this subsequence here. So all right, we do a partition 3.1 on the code, and we would want to say something like map v a particular function from A, B, C, like this. And then we want to say something like, if it's the case at so if it's an if the operator of C is a JNZ, and the maybe we should get the whole computer, because we want to kind of get the value in, yeah, okay, let's try getting the value. So let's say, and it's the case that the value in this state, so all right, keys as computer state code. Oh geez, since it's self-modifying, this is going to be tricky. Oh, this is going to be very tricky, because if I think we might have to do something like, all right, well, let's just see if we can implement something like this. So if the value is -2, then we know that we're doing like an add. So, oh, actually, okay, I think this can work. Even with, yeah, okay, this can work. So I think actually what we want is sort of like a look ahead. So let's call this look ahead. And then this will either return a new computer or nil. And if it's nil, then we'll just run the instructions as expected. So this gets the code out. Okay. So let's do a look ahead. So so we want to say that if this plus 2 is less than count code. Okay, then let's look to ahead. So let's put an and in here, and then let head be code add I in state. All right. Then say something like, if we know that there's a JNZ coming up, maybe we should, yeah. Maybe let's keep going here. If there's a JNZ ahead, so, okay, and let's say if it's hard coded to be -2. So because it might be, so if it's the case that arg A of a head is -2, so maybe we should say this instead. We'll say A, B, C, B, drop I state code. This better. And then so now we're looking at instruction C here. So in this case, so we have to keep looking for things. So we have to say, we have to ask whether it's an ink and a deck. So let's see. Let the stirs ink and deck be group by operator AB, like this. Then we need to say, if there's one ink and one deck, and hang on, let's take a look. So this is actually arg B up here. And the arg B, first of deck, is equal to the arg A, let's see here, Okay, then I think that's everything that we have to do. So yeah, so I think we've figured that out. Then what do we have to do? So we want to take computer, update. So we're gonna jump ahead 3. So so basically this thing. Okay, add 3. All right, then update in state. Arg A, whatever is arg A of the first of ink, we're going to be adding the value in the current machine state of arg A of the first deck, like that. And then update in like this, or I guess associate. We're just going to zero this out. So that's addition. Oh boy, this is a ton of code. I hope it works. Okay, so the other part of this if is just going to be nil. Yeah, so actually, yeah, so I'm not going to need any of this stuff here. And I can close this, so don't need this. Let's make this aligned. Okay. All right, so, oh boy, yeah, how do you even test something like this? Okay, and then, well, to plug it in, it's or look ahead computer. Otherwise, just do this. Okay. Okay, let's see if this didn't die immediately. I'm going to change this to a when here. And then some kind of okay. And then filter halted take 100, like this. Okay, didn't get any look ahead behavior. All right, so let's see. This number has to be less than the count of the code, so that should trigger. A, B, C, B, drop this from code, okay? If the operator is a JNZ and arg B of this, all right? Okay. So it should run all these, and then it should get here, and then it should recognize this situation. So, so that's actually so 1, 2, 3, 4, 5, 6, 7. Or actually, so this is going to be 0, 1, 2, 3, 4, 5, 6, I guess. So here, let's def cc computer this, and then let's try just taking 6. I think so. All right, and verify that look ahead on CC gives us nil. All right. Does this part work? Okay, so it's at 4. So 0, 1, 2, 3, 4. All right, so we actually need to go one more. Now it's at 5. And if we say this, it says nil. But it shouldn't. All right, so why not? So leave this out for now. Okay. Let's grab some of this here. So let CC like that. Okay, so let's do this first. All right, so we got that true. All right, so if, all right, then let's put in here. This is false. All right, is this part true? That part is true. It's saying that argb of C is not -2. Is that because it's actually this? Yeah, that's why. Okay. Okay. So maybe we can just change this to this. Evaluate. Now let's see if look ahead CC gives us something. No, it doesn't. All right. So let's go ahead. So this gives us true. All right. Then we have to do this group by. Ooh, that was ugly. Yep, I do like my editor, but sometimes does weird things. All right, so we'll put the if back in. And let's see. Now let's emit this. Okay, we got false. And that part's false. Is this part also false? No, that part's true. Okay. So arg A, let's see, needs to be equal to the arg. Oh, it's arg A. Yeah. Now it's true. All right. Now what about look ahead CC? Well, at this point now I'm confused because we should have everything. If this whole thing is returning true, then that means this should. Oh, right, because we have to. Okay, nice. And, okay, that's still on. All right, wrong number of args past 2. Okay, can work with that. Yep, right here. And also here. All right. Okay, so yeah, this seems like it might be doing something. Let's take 1,000 here. All right, seems like we're triggering a bunch of look aheads. Seems like we're triggering a bunch of look aheads. That kind of seems like a lot. Let's reopen the REPL. So do 10, I guess. Okay. Do 50. Yeah. Okay. All right. I think we're kind of working it. So let's take out this print line here, and I don't know, 5,000 steps. Yeah, and this might not be enough. Although this is probably a good time to run this now. Maybe it would have been nice to like save the state of the computer. Well, we're here. Yeah, I wonder if we can. It'd be nice if we could test it on verify it's doing the right thing. Okay, it looks like we got nil again. Yeah. Okay, so 500,000 doesn't get us there. Okay, then maybe we're going to need some. All right, well let's stare at the code a little bit. Okay, so there's this JNZ construct comes up a couple times. Comes up several times. Let's see. So don't bunnies usually multiply? Okay, so maybe there's a larger construct in here that does multiplication. Oh, there is. It's this one. It's this thing here. Aha. Okay. Oh, and it's here too. Aha. I wasn't ambitious enough in this gigantic in this gigantic look ahead function. So, all right. So if this is all the case, then okay. So what does it have to do? So it has to be the case that the next one's a dec, and the next one's a JNZ dec, or JNZ of that same thing, followed by -5. Okay. Let's just call this look ahead add, and then we're gonna define look ahead mult. Okay. Let's see. Is there a way to? Yeah, I'm just gonna do it this way. E like this, and we're gonna add 2 more things in here, which is basically the operator E has to be that, and arg -5. All right, and then furthermore, it's got to be the case that. Oh, hang on a second. I gotta figure out what this is actually doing. So, inc A dec C. So JNZ. So what happens? So what happens when we dec a? What happens when we dec 0? Just look at it. Update. I guess we just make it. We just make it a negative number. So in running something like this, so increment A, decrement C. Keep doing this. Jump non-zero. Keep doing this until C is 0. Then, oh, I see. Then C becomes, got it. Then C becomes, okay, and then it's just copy here. This is copying the value. So actually, so this right here, so this is actually part of it too. Okay, so we can put that in. Oh boy, I'll call this Z. Okay, so okay. So let's see. So now I need to check a couple more things here. I need to see if this is equal to this. So I need to see if arg-a of D is equal to arg-a of E. I guess I also need to check that D is a deck. So the operator of E. Okay. Then I guess I also need to check that there's some kind of copy going on here. That this is a copy into this right here. So and then I need to check at the destination E is equal to this right here, the deck. So first deck, like arg a, first deck, this. Okay. So when all of those things are true, then we're doing a multiplication. And this is the only situation that I see where so far we're going to need it, but I'm also thinking that this is going to get like toggled to it, because that's what toggle does, right? It's a toggle turns J and Z's into CPYs, right? Where did I implement toggle? Yeah. Okay, so this is going to do that too. So in that situation, okay, so what do we got to do? All right, the instruction pointer is going to be put ahead 6. Then, so let's see what. So this, so C here ends up as 0, and then and D also ends up as, so C and D end up as 0. So this the same as before, but then additionally, this is going to be arg A of the other deck, which is D. Okay. All right. And then this whole thing has the effect of making this be the product of, so let's see, we're going to get D copies of B. So that means D times B. So add to A the product of, so this thing doesn't mean anything. What matters is this thing. So we're calling this Z. So this is arg A of Z. and arg-a of, we're calling this D here. Okay. And then to plug it in, we're doing a look ahead mult, head add, and then so when we reach this situation, report it. All right. Yeah, let's try it. Okay, not recognizing this situation, but we should be recognizing the situation as early as here. Here, actually. So 2 before I was doing it before, and I was doing 5 before, so 3 like this. And then put this on. Okay, and okay, what is the I in the state of this? So 5, 1. Wait a minute. Am I not calling into look ahead mult? I should be. Am I not? Ah, okay. I never evaluated that thing. Okay. Okay. And yeah, let's go back to 5,000 on this. See if we can. Hey, all right, we're getting some multiplication. Hey, it finished. All right, let's try this. Right answer. Rank 64. Pretty cool. Pretty cool. Okay. Yeah, let's see where we got on the leaderboard. Here. 67th place. Not bad. Not bad. Yeah, let's do a review of the problem. So let's see. Go back. Got it. I am. Yeah. I wonder if. Yeah, I wonder if folks. I'm surprised so many people passed me. Basically, but anyway. Okay, so this problem is just an extension of the computer from day day 12 here, and we're introducing a new instruction, and the new instruction modifies code. So I think that one of the things that they did, one of the reasons that they add this was to make it a little bit more resistant to static analysis, like one of the problem solvers going in here and then just trying to figure out what this computer was doing. I don't know how effective it would be. I would have to watch the program in action. Anyway, so it specifies the behavior of this toggle, which is that basically it changes the operator. So that was I did a couple of things. One is that I changed the signature of do instruction to represent both the state of the registers and the code itself as a single map, and then that just made it easier to do things like this, and for the whole thing to return a new data structure. So yeah, so for these sorts of instructions, all that really is just where previously we were associating like a single value, now it's like nested in this state of the registers here. So none of these changed. The implementation of toggle ended up being pretty straightforward. So let's see, where did I put toggle? Up here. Okay, I'll get rid of this. So yeah, so one of the specifications of toggle is that you can't you can't toggle something outside the program. So I guess it never tries to toggle a negative instruction because I wasn't checking for that case here. But then, yeah, so then what it just does is it looks up that point in the code, and then it runs this anonymous function on it. And then the implementation is pretty straightforward, which is that if it's a single argument instruction, then it changes an ink to a deck and everything else to an ink. And then if it's 2 arguments, then it turns a jump into a copy and everything else into a jump. So yeah, so toggle was pretty straightforward to implement, and it gave us the right answer for our for the test case. And then, you know, as long as we knew that we had to initialize a to be a certain value, and gave us the right answer. Yeah, in the second part, it gave us a new value for the input a, and what is basically happening here is it's forcing it to do like a bunch of multiplications. So it just takes a while, and we noticed this in day 11. It's day 11, right? Day 12. But it didn't really matter because, you know, by the time like that I could have written that optimization, the whole thing worked anyway. But so anyway, in this problem, that doesn't work because you know, you'd have to run your program for probably quite a long time in order to get there. So what we do is we try to recognize the situation when we're about to like sort of enter a multiplication subsequence like this. And so I did notice here that this loop was adding the value of C to A, but what I didn't notice was that this is actually part of a larger loop, which goes like this, which is adding to A the product of D and B, and that's what this sort of construct in here does. Yeah, I wonder if other folks maybe used like fewer sorts of, because I wrote a lot of these conditions here, and of course getting the wrong answer because you missed one of these would be pretty bad. But I wonder if, like, in practice there are only how many instructions are there? Stop this. I guess if in practice there are only 26 instructions, then maybe it's possible to just sort of like stare at the thing. Another way to do it would be to sort of like observe the behavior of the processor over time, the code over time as it gets modified, and then maybe you find out that all the toggles go away. So then at that point, the program sort of reaches a steady state, and then you can. So the main reason that my first thought was what I could do is I could analyze the code and then just return a new sort of like code block, but that fails to well, it fails for a couple of reasons. One is can screw up jumps, and another is that it can screw up toggles. I guess for the jumps I could put in a no op, and you know, it just introduced like my own multiplication instruction. So maybe another approach to take here would be run the program for a little while. Actually, we can examine our final state here and find out if there were any toggles left. So so yeah, let's take a look. TGL. So there was a toggle left at the end of the program. So so yeah, it would have been tough unless you know, unless like this was wrapped in maybe I can substitute all instances of like a comma with a new line. Would this look? Yeah, it doesn't really look like it. So there was a toggle left, which means static analysis by a human is risky because you might not understand how the program is being modified. So anyway, so I implemented the adder, and then that didn't really do anything. Maybe I should have considered more carefully the hint here. But yeah, so this mega function is just it effectively is looking at, is trying to determine if we're in a situation where where we can optimize away a bunch of instructions, and this is just checking a bunch of things about the code structure. I've never written an optimizing compiler, so I don't know if this is if there's like a much more elegant way to do this. I'm sure there are better approaches, but I don't know them. And in the end, it turned out to be good enough to give us our answer. We ended up getting it pretty fast here. Yeah, 7 milliseconds. Yeah, it's pretty fast. So, yeah, I wonder if yeah. So I'm curious to see what other approaches people took to solve this. Let's take a look at our advent calendar. Okay, very nice. Looks like this tower here will get a little Christmas tree, which I'm happy to see. And yeah, tomorrow's problem will be the Christmas Eve problem. It'll be the 23rd here in California, but only 2 days left. Getting very exciting. Having a lot of fun with it, and I hope you are too. And I will be back on tomorrow for problem 24. Thanks for watching.